All right. Just a few more seconds before our official kickoff time. Uh, okay, here we are, Berkeley time. Welcome back, folks. So today, the main order of business is to finish off our lecture on texture sampling. I really like this lecture. I really think this material is super neat and mathematically, intellectually, and is really at the core of GPUs and real-time graphics. So I want to teach you a lot of stuff today in that area that I think is, it's really foundational, and I hope that you enjoy playing around with it in the assignment as much as I'm looking forward to teaching it to you. And then we'll get on to some stuff to do with shading and the graphics pipeline as well. Okay, last time I wrapped up by getting to the next slide after this one, that observing that applying textures as sampling. I showed you this slide, which described exactly how that works. So for every screen space sample XY, we figure out the UV coordinates in a texture image corresponding to that screen sample location. We then look at a texture image object at those UV coordinate positions. When I say look at, I literally mean we sample inside that image to get the value of that texture image of that location, and then we draw it to that frame buffer location. So this is really, exactly to the definition of sampling that we've seen in the past. And actually, it's actually something that we call resampling. It's like a sort of it definitely is sampling. It's sort of a specific type of sampling that's going on that has a bit more structure. So mathematically, one way you can think about it is that to draw a texture sample at a position UV, a few things have to happen. First of all, we have to have the texture image to start. And if we start with like a photograph, like an image file that's an array of pixels, of color pixels, then you can think of that as a sampled discrete 2D function where we only have a color defined on a grid of pixel locations, okay? And mathematically, you can think of this as not defined or zero everywhere else that's not on those grid locations. So to sample it at a general UV coordinate that might be at a continuous position, we have to first reconstruct a continuous function. We could call that f continuous. And the way you can think about reconstructing that is to take the discrete f image, again, that's the pixel image, the texture image pixel locations, and convolve it with some kind of function to reproduce a smooth function. Convolve in this case by a function k that we call the reconstruction filter. Then we can draw the desired sample at position UV by evaluating the continuous 2D signal. So we can evaluate okay, so that's sort of what's meant by resampling. Hey, Rishi, can you help me to take a look at if we have a feedback loop or something because of maybe someone accidentally unmuted? Thanks, Rishi. And as I mentioned last time, the signal processing concepts that I want for you to bring up in your mind when you see something like sampling or resampling of this kind is things to do with what we talked about in rasterization and sampling anti-aliasing. So frequency spectrum, aliasing, Nyquist frequency, filtering at high frequencies to accomplish anti-aliasing, these kinds of things. So what I want to do for the remainder of today is to show you how that plays out when we're doing texture mapping, because there's a lot of really interesting structure in it that's more sophisticated than what came up in rasterization, but it's going to build on what we talked about there. So let me start by showing you an example of what aliasing looks like when you apply texture mapping without anti-aliasing, okay? Point sampling textures. On the left, what you see is a rendering of a very simple scene. It's like a ground plane that has a blue grid texture that's drawn on top of it, okay? So it's just these blue lines. It's just drawn from a texture and laid on top of the ground plane. There's perspective, so it goes off to infinity. And why this is a nice test scene is you can see, if you're thinking in terms of frequency, again, right, the rate at which the signal is varying, you can see it varies really quickly in the background. It's going to go blue and black really, really quickly in the background, okay? And this is an anti-aliased image. We'll talk about how that was accomplished as we go through the lecture, but this is a high-quality anti-alias reference. It's also high resolution, 1280 by 1280 pixels. I'm going to show you what it looks like on the right-hand side, and in this image, it looks a lot worse. Okay, that's the first observation. Let me tell you exactly what's going on here. The image is lower resolution on the right-hand side, 256 by 256 pixels. The only reason I did this is so that when it's at low resolution, we can see the aliasing artifacts more visibly, okay, for us to talk about. But the reason it looks so bad is not because of the low resolution, not primarily because of that. It's because we're point sampling the texture. And what that means is that for every position on that ground plane that we draw, so every pixel there, we take its XY location after rasterization, and we calculate the UV coordinate in the ground plane blue grid texture, and we look it up in that blue grid texture. But we only do that for one location. And if you think about what's happening in the background, right, that one UV coordinate location in the background, which is almost going to be randomly blue or black in the background because it covers, it's varying, it's such a high frequency rate, as you can see on the left-hand reference, it's just going to produce almost a random black or blue value, which is exactly what you see happening in this image at the horizon line. So it manifests as moire in the background, the aliasing area does. And in the foreground, we see other effects. We see the jaggies that we're familiar with. Okay, they're showing up here. So these are the kinds of things that happen when we look at aliasing and texture mapping. I want to get into all the details of what this is and try to dissect it a lot more. Okay, so let's talk about texture sampling frequency. And I want to look at an even simpler example of what's going on for you first. Let's consider what happens when you draw a texture image. In this case, it's just a photograph of this insect here, this damselfly. We're just going to imagine drawing it onto the screen and see what happens when we draw it either, you know, at its natural resolution on the screen, or when we magnify it so it looks bigger on the screen or occupies a larger number of pixels, or we minify it and it looks at a smaller number of pixels. That's going to change the sampling rate in the texture image. And let's look at exactly what happens there. So this is, first of all, the natural resolution of drawing it on, if you will, onto the screen. It's a 1-to-1 mapping. What does that mean? On the screen here, so in screen space, 600 pixels across, matching in the texture space, that is in the texture image, 600 pixels across. On the bottom, what I'm drawing for you is just, think of it as a super zoom in. This cartoon is a super zoom in of the sampling rate on the screen in red dots of the screen space pixel locations. And on the right-hand side, the white open circles are the sampling rate of the pixels in the texture image. And when we draw 1-to-1 like this, you can see, right, it's very intuitive that every screen space location, every pixel that's drawn is just going to pick up from exactly one pixel, each neighboring pixel inside the texture image. And I'll draw it for you as a cartoon. What happened to my slides here, like this, okay? So I've just drawn it to show that every pixel on the screen is going to map from exactly one pixel in the texture image. When we say texture here, yeah, texture is jargon, okay, in graphics for meaning an image, in this case, an image that we're going to map onto geometry, as I defined at the beginning of last lecture. Okay, so for texture, just think of it as the image that we're going to draw onto the 3D objects in the scene. Let's look at what happens when we magnify. This is what I mean by magnification. So let's take a moment here to see exactly what happened. In screen space, what happened was that the damselfly now looks zoomed in, right? It looks larger in the screen, okay? So even though this patch of the screen is still 600 pixels, we see a smaller portion of the texture image. This is what we call magnification, okay? Or the magnification case in texture mapping. Now, what's going to happen in terms of every pixel, the density of pixels as we take them one by one here in the screen space? We figure out what the UV coordinates in the texture image are that we need in order to draw the image on the left. What's the sampling density going to look like in texture space is what I want you to think about. Okay. Had a moment to think. What do you think the red dots? I'm going to draw each of these red dots projected here. We're just thinking about the density. What's it going to look like? Here's what it looks like. Keep losing light. Here we go. What does it look like? It looks like this. Is that what you're expecting? So every dot here that's somewhere on the screen, we figure out its UV coordinate and it maps somewhere in here, and I'm plotting it over here. And these neighboring screen space samples will turn into neighboring samples here, and they're at twice the sampling frequency of the pixels in the texture image. Okay, let's keep going. What if we go the opposite direction? This is called minification. Okay, minification because we're drawing on the screen now the damselfly image smaller than it appears naturally. Okay, so 600 pixels across here. Now we're drawing the whole damselfly image only across 300 pixels. What's the density going to look like in the texture space here? It's the opposite. Okay, so every screen space sample here will project, as you can see here, one by one, and they're going to be one texture lookup across every two texture image pixels. Now, at this point, you can be thinking of like, I want you to be thinking of like, okay, sampling rate. And then we talked about Nyquist. Now, when are we safe? When are we not safe? And remember, I tried to say that aliasing is happening when we sample at a rate that's too slow compared to the highest frequency changes in the signal. Okay, if we sample too slowly for high frequency change, we're going to have problems. We'll have aliasing. Anti-aliasing was about filtering out high frequencies, getting rid of the high frequencies before we sample. Okay, so that might already start turning the gears in your mind to think about like what's what is going on here, where we're going to have the worst aliasing sort of cases. And actually, I want to just note this will depend on your Zoom resolution. You can look at a full resolution afterwards on the web if you don't see what I'm about to describe. But if you look at it here and you see it as clearly as I do, you'll notice that on the screen space image on the left-hand side, this damselfly image is quite aliased. You can tell by looking at the fine detail structure in the wings and observing that a lot of these lines are now broken up. You can actually see jaggies in there, and you can actually see gaps in the lines themselves because they're too fine. They're varying at a too higher frequency in the texture image. So after they're being projected onto the screen and we're sampling them at a lower rate, aliasing is coming in. Thanks, Rishi. So texture sampling rate. The sampling frequency in the screen space will translate to a sampling frequency in the texture space. And that frequency is going to be determined by the mapping function. The mapping function was what I defined at the beginning of last lecture, which says, for the location on the screen via the 3D geometry in the world mapping to locations in the texture space, like that mapping is what's going to determine the rate at which we move there. In general, that frequency varies across the scene depending on a lot of things. We should note that it's quite a complicated mapping here in general. It can take on a lot of different nonlinear, characteristics. It depends on the geometric transforms in the scene. It depends on the curvature of the geometry in the scene. It depends on the viewing transforms. It depends on whether we have perspective or not. And it depends on the texture coordinate function that we're laying over the 3D geometry in the scene to say, hey, at every position on that geometry, what's the UV coordinate in the texture map? All of those things will come together to determine this final mapping and determine the final frequency sampling rate in texture space. But there will be a specific, at any point in the rendered screen image that maps into texture location, there'll be a specific sampling rate at that location. At optimal viewing size, we'll have a one-to-one mapping between pixel sampling rate and the texture sampling rate. They'll match. And the one thing I want you to observe right away is that that's totally going to depend on the texture image resolution. If we use a 512 by 512 image and they map one-to-one, well, if we used a higher resolution image, say 1,000 pixels by 1,000 pixels, then it won't match one-to-one, right? So this is going to depend on the resolution of the texture images that we're using here. When it's larger in the magnification case on the screen compared to the texture, as I showed you in the previous slides, we'll have multiple pixel samples per texel sample. Texel is just a short name for texture pixel, okay, a texture image pixel. That's what a texel is. When it's smaller in the minification case, one pixel in the screen will sample multiple texture samples, texel samples, okay? So if the image that I'm showing you here on the background with these gray dots is the texture and the texture pixels, then you can think of the footprint of the screen space pixel. If you think about taking its square outline, so to speak, and projecting it via the mapping onto the texture space, you can sort of think of its relative size. Now, I drew it here to show that it can vary in size and even in orientation. In fact, it could even end up being curved. It could be very small in texture space. It could be very large in texture space. And these things will all result in different sampling rates. Let's take a look at this image again that I showed you earlier, okay? I see a question about super sampling. I like how you're thinking. We're going to come to that in a little bit and consider what happens in super sampling with respect to texture mapping. But great intuition. You're looking ahead to anti-aliasing, the problems that are inevitably going to arise here. Let's look at what the textures pixel footprint looks like for this scene I showed you before. Okay, so here's like 5 different locations in the output rendering. and I'm mapping them into the texture space. So the texture space is just this blue grid, right? That's the texture image. Take a look, it varies a lot, okay? This pixel here, which is close to the front of the screen and in perspective here, is a pretty small projection onto this blue grid here. You look at it here and see, yeah, it's a tiny texture pixel projection into texture space. In converse, this one over here, if we had a screen space pixel over here, you can see that it's covering many, many blue lines in the grid. And sure enough, when you look at its projection into the texture image, it covers a large area in texture space, okay? So note, the texture sampling pattern does not have to align with the XY axes or the vertical horizontal axes of the texture space. It doesn't have to be isotropic. Isotropic would mean the same in horizontal and vertical directions. It can be quite tilted, quite rotated in space, and it can be very stretched out. Okay, so that's interesting and creates a lot of sophistication to the problem that we're looking at, and challenges for engineering the anti-aliasing in good ways. Let me observe here, is a sort of a more mathematical footnote. You can estimate the footprint area of this projection, if you think mathematically, via the mapping function. So if in screen space, there's a position, say vector X, say for XY position, and it maps into texture space, texture UV space, via the mapping function psi that I defined at the beginning of last lecture, then psi of X will go somewhere in that space, and you can think of the differential change, right? With respect to X and Y change in the screen space, according to where they will map into the texture space via psi and the gradients of that. So you can observe that this line here, or sorry, this vector here will be day U day X, comma day V day X, and similarly for this other direction here. So you can actually estimate the area of this change here by using these derivatives of the mapping function, okay? We're going to come back to that later because we'll actually want to do that to estimate it directly in order to quantify, how to do the anti-aliasing, okay, correctly. They'll be related, allow us to estimate the required sampling rate, not too much, not too little, in order to retain detail, but not to allow aliasing. Let's start talking about texture anti-aliasing itself. Sort of, I mentioned some mathematical stuff. We're going to go all through the details of that, but let's try to get some intuition. Someone already asked, I thought, a really useful question. Hey, we've already talked a bit about this, right, in the context of rasterization, and we talked about how supersampling is an anti-aliasing scheme. So will supersampling anti-alias texture mapping? And the answer is definitely yes. So here's the point sampling case again. It's one sample per screen space pixel that I'm showing you on the right-hand side. If we supersample, say 512 times, so 512 samples per pixel, yeah, it will anti-alias this scene. Now, you might say it looks kind of blurry on the right compared to the left. Now, remember, the left is a high resolution reference. On the right-hand side, we're deliberately looking at a lower resolution thing here, 256 by 256, just to look at what's happening in terms of aliasing error or aliasing artifacts. So this is actually a really high quality image on the right-hand side. So anti-aliasing will produce a great result, but think of how expensive this is, okay? This is requiring 512 times the computation, right, at every pixel that's outgoing here. So texture anti-aliasing, will supersampling work? Yes, but costly. And when we're highly minified, such as in the background cases here, right, one screen pixel here can cover many, many blue lines, right, in this grid because it's so far off towards the horizon, which means it can cover a very large area in the texture image. That's a very high degree of minification of that texture image onto the screen. When very minified, you might have a lot of texels. Again, those are texture image pixels, right? A lot of texels in the pixel footprint, and you might have to do a lot of supersampling in order to anti-alias. So the goal I want to talk about for the rest of this lecture is that supersampling is not a very common scheme for getting rid of texture aliasing because it's too inefficient. I want to talk about the efficient texture anti-aliasing methods that have been developed. We want anti-aliasing with only one or a very small, finite, constant number of texel samples per output pixel. How? Again, anti-aliasing is filtering before sampling. So we're going to somehow here be filtering the signal before sampling. Okay, that's where we're going. Now, anti-aliasing, so I said filter frequencies before sampling. And remember, sampling rate, we want it to be commensurate with the Nyquist rate so that we can be safe from aliasing as sort of our engineering guiding light. So signal, sampling rate, Nyquist rate, what is the signal in texture mapping? The signal in texture mapping is the texture image itself. That's the thing that we're sampling, okay? What is the sampling frequency? As I said, the sampling frequency, there's one in the screen space, but each of the screen space samples is going to project via the mapping into the texture space. So the sampling frequency that we care about on the signal we care about is the sampling frequency in on the right-hand side here in texture space. What's the Nyquist frequency? What's the highest frequency in a texture image? It has to do with the resolution of the image, right? The higher the resolution of the image, the more detail we can put in there, the faster the rate that we can make that texture image have detail that goes up and down at a high frequency. And so we want to relate the sampling frequency in the texture space, and we can think about controlling it by controlling the resolution of the images in that space. Let's look at an example. Actually, I see. Sorry, hold that thought. That's going to be most important when we talk about minification, which I'm going to come to in about 5 slides. That turns out to be the much harder case to deal with anti-aliasing wise in texture mapping. Okay, well, it might be a bit surprising. The hard case for drawing nice textures, nice good-looking textures without aliasing, is actually the minification case, which means we're drawing it smaller on the screen than the texture image resolution that we have. Okay, I always found that counterintuitive when I first learned about texture mapping, but that's a fact. We'll see why. First, let's deal with the easier case, texture magnification. Now, the first observation is that you usually don't want this. Okay, what this means is that you don't have enough resolution in the texture images that you're using, right? Because if I want to draw on the screen, but I only have, say, 512 by 512 textures, and I want to draw on the screen at 2K by 2K, well, you know, it's going to look a little blurry. I mean, there's nothing you can get away from because there's not enough resolution in the texture images. So the first solution would be to go and try to get higher resolution textures in order to avoid this problem. But it will inevitably come up as you zoom into scenes and magnify. So what do you do in those cases? The best you can, we just image interpolation. And you'll see the kernel function here. The kernel is the reproducing function that goes from the sample discrete texture image pixels and interpolates them up, right? So produces a continuous function. If we use nearest neighbor interpolation, that is wherever there'll be sample and texture space, we just go to the nearest texture image location, or a texture image pixel rather, and just choose its color. Then you'll see blockiness because you're going to the nearest one. And you can see that in the leftmost image here. If we interpolate between the nearest 4 pixel locations linearly, that's called bilinear interpolation. You'll get an image that looks like in the middle. If you use a smoother interpolation called bicubic, which uses cubic interpolation polynomials, we'll talk a bit about that when we get to geometry portion of the course. But for now, just know that it can be a smoother interpolation. You get something that looks like the image on the right-hand side. The observation I'll make is that nearest looks a lot blockier. So unless you're going for this to be able to let people see the pixels themselves, then usually bilinear is something that is used to smooth things out. And between bilinear and bicubic, there can be an improvement, but it's pretty subjective. So let me tell you about bilinear filtering. Okay, how does bilinear filtering work? It's really common, really useful. If you want to sample a texture, a value at position UV here, continuous UV position here, then, and the black points here represent the texture sample location. So those are the image pixels in the texture, right? How do you do it? Well, you can go to the nearest 4 pixels here, and then we want to linearly interpolate between them. So how does this work? We can look at the fractional offsets, S and T, that are shown here. Okay, so here, if we consider between this pixel location and this pixel location, if this was 1 unit, then S here as a fraction of that is the horizontal distance from horizontal distance of the sample that we want to draw, the sample location, and similarly for T in the vertical direction here. Okay, so what do? We linearly interpolate between the two of them. Okay, so linear interpolation, let's define a helper function. We'll call it lerp for linear interpolation. And we can say that, hey, if I give you an X location between 0 and 1, X value between 0 and 1, it could be either S or T, as we'll use it in a second, but we define X between 0 and 1, lerping between V0 and V1, value at the beginning, value at the end. Then we'll define it as V0 plus X times V1 minus V0. This will linearly interpolate between V0 and V1 as we go from X being 0 up to X being 1. We can use this lerping function, an extremely useful and almost ubiquitous function to use in graphics and lots of other applications, by doing two helper lerps first. We can first do a lerp on conceptually the bottom of this rectangle. Okay, so from U00, 0, which is the value of this texture image at this location, and U10, which is the pixel value of the texture at this location. We can lerp between U0 and U10 with S, which is the partial distance here. And we can do it the same up here, conceptually on the top of this little square here, between U01 and U11, as shown over here, and give ourselves values conceptually that are at this location and this location, which will say have values U0 and U1. And then lastly, we can take a final lerp in the vertical direction between U0 and U1 using the T value here in order to interpolate from here, moving towards the top of the square, and get the final value at this sample location here, f of xy being the lerp with value T between U0 and U1 as defined here. Is lerp just a way to represent a linear interpolation function? Yes, you got it exactly right. Okay, so we do 3 linear interpolations here, and then vertically is the way to think about it. All right, so this is bilinear interpolation, and we can use it for bilinear texture filtering. And I showed you the results of what it looks like. Again, it looks like this. If you use nearest neighbor, just don't do any linear interpolation, just pick up the pixel value that's closest to you. You get an image that looks like the left. I put a couple of questions here. I'm going to leave it for us to take up in comments on the website so I can keep moving. Okay, so that's the easier texture texture reconstruction and sampling case. Let's talk about texture minification, where a lot of anti-aliasing issues will really come up. Okay, this is the hard case, texture minification. Drawing the texture image onto the screen at lower pixel resolution. It's challenging because there can be many texels, many texture image pixels that project into the same screen pixel footprint. The shape of the pixel footprint can be complex, okay? As I showed earlier, it doesn't have to be, a simple square. It can be a funny trapezoid. In fact, in general, it can be a curved quadrilateral in texture space, or even more complex than that. If the geometry in your scene is very, very tiny. What's the idea? What's the idea in texture minification anti-aliasing? What the idea is to take the texture image file and then low pass filter it. What does low pass filter mean? Again, it means passing only the lower frequencies in the space, filtering out the higher frequencies. So low pass filter and then downsample it. Downsample just means sample that signal at a lower rate, okay, a lower resolution, and do that recursively. So we take the original image, we low pass filter, take out the high frequencies. That means to blur it a little bit. Downsample it. That means sample it at a lower frequency, get a lower resolution image, and then do it recursively. Blur it again a little bit, reduce its resolution by downsampling again. Blur it a little bit, downsample again. Okay, that's one of the core ideas in there. And then for each sample that we draw from texture space. The idea is that we're going to determine which texture file to use, which texture image file to use that has the resolution that approximates the screen sampling rate. And you see what we did there? There will be some resolution that's the closest to drawing it onto the screen at 1-to-1 pixel resolution, which I observed as sort of the nice case, right? The natural case. And we're going to use this pyramid of different image resolutions to provide us a way to just look up in a particular image, the one that has the right sampling rate. Okay. Let me show you a picture of what this will look like. Okay. Let's see what doing this kind of sampling with different image resolutions is going to look like. Level 0 is the name we're going to use for full resolution texture. Okay. This is an image of the Sponza sort of test case that I showed you last time, where all the textures are being drawn on the screen, sampling only from level 0, the full resolution textures. And what you can see is a couple of things I want to point out. First, in the background, you can see this aliasing. If you don't see that, I apologize. It's a Zoom transmission thing. You can see it in full resolution on the website. What I see is in the background, you can see the brickwork, and you see lots of aliasing in that there's gaps in the grout. Okay, like the gaps between the brickwork is not clear. In the foreground, in contrast over here, things look good. Okay, there's a lot of detail, but it's not aliasing in the foreground. Let's go to level 2. Level 1 is going to be downsampling 2x2. Level 2 is going to be downsampling 4x4. So now we're using image textures that are 16 times smaller in pixel number compared to level 0. What do I see? I actually still see aliasing in the background a little bit. It looks slightly less bad, but it's still there. In the foreground, I see blurring. Okay, let me go back for you. So this is the original. You can see a lot of detail in the foreground that becomes blurred when we go to level 2. In the background, there's aliasing that is less bad than level 2, but still there. Let's keep going. This is level 4. I'm skipping a couple levels here just to make it go a bit quicker. At level 4, we're downsampling by 16 by 16 pixels. Okay, so compared to level 0, we're 256 times fewer pixels. Okay, 256 times smaller texture image. What do I see? In the foreground, okay, there's a huge amount of blurring. This is a really low resolution image that we're using now here to texture map everything. Okay, so we see a ton of blurring in the foreground. But in the background over here, we can see that aliasing is gone now. It's okay. This is intuitive, or you can think of this, I hope, in an intuitive way by saying that, look, in the background, the brickwork that we're drawing is really far away. We only need a really low resolution picture of the brickwork to draw it on there, and it'll look right. In fact, if we try to draw a high resolution image on there, we're going to have aliasing, okay? But in the foreground, we can't use just a low resolution image. We need a lot of detail, okay? Because it's pretty close to us and we can see all the pixels in the texture directly. So we need a high resolution image. So what we're going to want to do, of course, is neither of the 3 pictures that I've shown you here, not level 0, level 2, or level 4 for the whole image. We're going to want to choose the level in the texture pyramid based on which part of the screen we're drawing to and what the sampling requirements are at that specific location. Okay. Let me show you a picture of what that texture image pyramid looks like. This is a really famous data structure actually in graphics, okay? It's still in heavy use today because it captures a lot of the core parts of anti-aliasing for textures that are most important. You can do better than this. This is not like a perfect solution. It's just a great engineering trade-off, okay? And so it's still very, very useful. There are methods that you can do to get higher quality results than this. I'll touch on those later. But this is called a mipmap. A mipmap. It's actually a really clever name. It's stood the test of time. There's been a lot of other terminology that's come up in graphics and visual computing that riffs off this term mipmap, okay, and have other names that are sort of go with it sort of its style of naming things. It comes from mip, from the Latin multum in parvo, which means multitude in a small space. Okay, and it turns out that this is a great name for it because we're going to contain a lot of great information for drawing anti-alias texture maps onto real renderings, and we're going to store it in a very memory efficient manner. Okay, so let's take a look at it. Let's say that level 0 here started at 128, 128. These days, you're much more likely to use a very high resolution texture, 1K by 1K, 2K by 2K, okay? But I just shown you here with a low one, so fit on the screen. All we do is at each successive level, level 1, then level 2, then level 3, as you can see, we just decrease the resolution by a factor of 2 in X and Y. Okay, so 128 by 128 goes to 64 by 64, 32 by 32, and so on and so forth. And you can see we actually take it all the way down to 1 pixel. Level 7 is, it's a 1 pixel texture, constant value texture, just purple. Okay, the average color of this whole image. Okay, so that's what a mipmap looks like. Now, you might say, well, okay, so what's the size of this mipmap image? You might sort of remember like the sum of a geometric series, okay? So, you know, like the kind of problem you might have done in like in a high school pre-calc or a calculus class or something like that. Anyway, you can figure it out, all right? It's not a big deal. It turns out it's not a lot more space than just the original texture image, okay? It turns out it's only 1/3 more area, 1/3 more memory, or 1/3 more pixels in aggregate for the whole pyramid compared to the highest resolution image, which is a nice property to have. Which level of the mipmap should we use when we're drawing to the screen? That's the next question that we need to answer. This is something that you're going to calculate in your assignments. Okay, so you're going to implement code for this, unless you happen to write perfect code, which may happen on this because it's not that much code. But usually, I don't know about you, but like most people find that when you write code, usually there's more likely there to be a bug than not to have a bug. So you might have to play around with this math and your implementation of it and see what happens visually, okay, in your images, which will be like how well is it anti-aliasing or not, by your calculation of the mipmap level D here, which is the level in the mipmap pyramid that will go to look up the f of uv value that we want. What values should we pick? Now, again, remember, if you're drawing to the screen, say a triangle, let's say there's some perspective transform in the scene, okay, then what does it look like in texture space? It might look like something like this as an example, okay? So here are 4 blue sample positions inside the triangle. They map to these texture locations. These here might map to these red sample locations in screen space may map to these texture locations in UV space. These are going to require us to look up different mipmap levels, okay? The larger the projection in here, then the higher the mipmap level that we're going to want to go to, because we want to go to lower resolution texture images. So estimating the texture footprint size here in texture coordinate space of neighboring screen samples, which is very related to that Jacobian observation that I made earlier mathematically, is a way computationally for us to estimate which level. What is done by convention, although there are different trade-offs that can be made, and you could explore them very easily in your code when you get to this part of the assignment if you wish, is to calculate D as, okay, first of all, as using a value L, which I've drawn here. This distance here is L. We'll come back to it in a second. Okay, what we do is we take the log base 2 of L, and that gives us D. D is the mipmap level. Let me just back up a couple of slides and remind us why we would have a log 2. Oh yeah, it's just because remember each of these log levels here is decreasing the resolution by a factor of 2, okay? And level 2, level 3, level 4, level 5 is in a log 2 scale, okay? So that's the reason that we end up with this log 2 here. So what is L? L is basically the number, it's a length in pixels at the original resolution, okay, the highest resolution, level 0 texture image. Now, this has to do with these 4 samples in red here that are projected here, and I've chosen one of them, as you can see here. And actually, it's going to be the longer one is the convention that's chosen between this vector here and this vector here. That's geometrically what's going on. That's represented by this max, okay? The maximum length between this guy and this guy. So everything that's in here is just this quantity here is just the length of one of these vectors from the partial derivatives of du dx and dv dx, okay? So these are the vectors that are drawn here. So this is just by Pythagoras theorem, the length of L for this guy or this guy, and we take the max of those two. Now, so what's going on here? Basically what we're doing was trying to estimate the length in pixels of the projection of neighboring screen space samples after they've been projected into texture space. If it's one-to-one, it means that we'll just sample from the highest resolution texture. If it's a very large number of pixels, like 8 pixels across, okay, for this L, then we're saying, hey, we need to go to a lower resolution texture. How much lower resolution? Well, one that's 8 pixels for every 1 pixel originally on the screen, okay? Oh, so we should go down to a lower resolution by 8 by 8. So L would be close to 8 in that case, and log base 2 would tell us to go 3 levels down in the mipmap hierarchy. This is the reason why this math comes up in this particular kind of a way, okay? And do I have one more slide? Okay, yeah. You can also think of this as this kind of a picture. L can be sort of like the this distance here, which is like the area. You can think of it as related to the area of like a pixel if it was pixel aligned in this case. Let me visualize for you what this looks like when you apply it to that scene that I showed you before. If you calculate D according to that formula I showed you before, and then visualize each of those D levels as a different color here, you can see that it's going to vary. In this case, blue at the back is for higher D values, lower resolution images. In the foreground, red corresponds to lower D, lower levels in the mipmap, which correspond to higher resolution texture images. You'll notice also that if you just calculate D and round it to the nearest integer levels, you're going to have breaks in the scene from where you pop from one level of the hierarchy, one resolution, and then you jump to start using image at the next resolution. If you think about that, that's actually a high resolution or a high frequency change of its own. Okay, we're sort of in a very fast way changing from one signal, which is at one resolution texture image, to another one. If you're developing a sense of aliasing, anti-aliasing, these kinds of things, that should worry you a bit from an aliasing perspective. And it turns out that if you have that intuition, you'd be right. If you try to do nearest D, rounding to the nearest integer level for D, and you try to render like a camera flying through the scene, you will, if you pay close attention, notice some kind of discontinuity happening at the boundaries of where these integer changes are happening. So we can smooth that one out too by doing another layer of filtering. Let me actually skip one slide and show you what it looks like. We could blur it out, okay? We can use a continuous D value. Those calculations I showed the math for D didn't require being an integer value. You're gonna get a continuous value, and then we can find the nearest two integer values. We could do this texture sampling from each of them, and then we could interpolate between the two of those levels. That's called trilinear filtering. It looks like this. We calculate the D level, you find the mipmap level D for below, and then D plus 1 above. I should actually say floor of D, and then floor of D plus 1, okay? And then you can do bilinear interpolation here, get a color. Do bilinear interpolation at the next mipmap level, get a color. That gives you two colors, and then we can linearly interpolate between those two colors based on the continuous D value. And if we did that, then we end up with a scene that looks like this. And that smooths out that boundary too. This is also an attempt to anti-alias, okay, to knock out the high frequency change at that integer boundary before we perform this sampling. Now, I said that, look, this is really common. This is the backbone of how texture mapping is typically done in a lot of high performance graphic systems. Actually, this is sort of the backbone of typical higher quality filtering that happens these days. I'll sort of mention that you could take multiple samples in a mipmap or something that's closely related in spirit to a mipmap, and in order to perform a finite number of computations, that's going to give you a very high quality result. Trilinear filtering, though, is a very good approximation that yields great results. Let's figure out how much it costs to do. Bilinear resampling requires us to look up for pixels in the texture image, and then we have to bilinearly interpolate them. That's 3 lerps. Each lerp is a multiply and 2 adds. And okay, so anyways, that's bilinear resampling. Okay, so 4 lookups and then 3 and then some arithmetic. Trilinear resampling is 8 texture reads, right? For 2 levels. and then 7 lerps, 3 in each of the levels, and then 1 additional between the levels. So you get 7 multiplies and 14 adds. Okay, so where do we end up? Now, this is a far cry from having to do a potentially unbounded amount of super sampling in order to knock out potentially arbitrarily high frequencies, as I showed you earlier, as a super sampling sort of approach. Okay, so this is why MIP-based texture mapping for anti-aliasing is so important. On the assignment, we're going to have you explore this. Okay, we're going to get you to just implement and look at the different combinations of this. You'll implement trilinear interpolation and then just turn off different parts of it, okay, to explore what happens when you leave it out. So for image resampling choices, you'll do nearest neighbor versus bilinear interpolation, see what that looks like. And then for the MIP-map level choices, you can do always level 0. That's equivalent to having no MIP-map. Nearest D, integer, and then linear interpolation, as I described earlier. If you do linear interpolation here and bilinear, that's trilinear MIP-map. And that's, as I said, a very high quality result. But it's not perfect. It's a very high quality result. It's very efficient, and it gives good results that are very robust across a very large number of scenes, but it's not perfect. This is super sampling 512x compared to point sampling. And this is MIP-map trilinear sampling. It eliminates jaggies in the foreground. It knocks out moire, all those other kinds of things. But if you look closely here, you'll notice that it overblurs. Okay, it's over blurring here. Why is that happening? Why is that happening exactly? I think this is a really good thing to think through. The answer lies in sort of the geometric diagrams that I've shown for the shape of the footprint at different points in this exact image. I showed what those slanted footprints can look like, and then reasoning through what the calculation of the D level looks like. I encourage you to think about that as you're doing the assignment, and then think about this slide and that relation, and we can chat about it on the website, okay, as we're working through that. Let me mention, you can use the MIP-map in related techniques or variants of this MIP-map pre-computation to do things called anisotropic filtering, where the filtering density is not the same in one X direction versus the Y direction, for example. This is a result from elliptical weighted averaging, average filtering, or EWA filtering. There are also things called RIP maps and summed area tables. This is an example of a RIP map, I believe. These are actually not that common. Yeah, I believe this is a RIP map. This is a visualization of applying EWA filtering, where you use multiple lookups in things like a MIP-map hierarchy, and then weight those different lookups in order to approximate adding up the pixel values in the texture map according to arbitrary footprints, okay, in the scene. All right. So what I got to say about core 2D texture image sampling, which, as I said, is a really common foundational technique in graphics. This is used everywhere and involves a whole bunch of really interesting engineering in order to, that requires basic engineering related to anti-aliasing. Otherwise, you just do not produce reasonable looking images. They'll just alias terribly and they'll look awful, okay? We've covered those sort of core foundational pieces. I want to now switch gears and finish up this texture mapping lecture by showing you, or just touching on a whole bunch of different texture methods and show you the diversity of techniques that are similar in spirit to 2D texture mapping as we've looked at in detail, but they're applied in many, many other ways that give you a lot of creative power in modeling different worlds or implementing different visual applications. The way that you can think about it, I want to encourage you to think about it in general, is that in modern GPUs, texture mapping, you can think of it like memory, general, memory in the GPU plus filtered lookup. What was filtering again? It's all this anti-aliasing stuff that we just talked about, okay? It's a general method to bring data into fragment calculations. Fragment, you might remember I described, was basically a name for like a sample, okay, in rasterization. It's a general method to bring high frequency data, high resolution data with anti-aliasing backed up by GPU memory lookup hardware into those fragment calculations. There are many applications. Some of the names are environment lighting. You can store microgeometry in it. You can define procedural textures. You can do solid modeling. You can do volume rendering. Let me show you a bunch of visual examples. The first one is an environment map. So in this part, the way I encourage you to take it is to let it sort of wash over you by getting a sense of a bird's eye view on the diversity of kinds of methods of applying texture mapping like computations. And then I'll talk through some specifics so you can see how the diversity of those kinds of things, what the visual appearance of those kinds of things looks like. This is a technique that is an attempt to define the color of the environment, not directly the color on an object. So we're not taking an image and pasting it onto an object. We're taking an image and saying, hey, you know, if you were just looking out all around you, what would you see? Oh, if you can see it, this is an environment map. The answer to that question would be, if I look around, I'm inside a room. Okay, I can see the four walls of the room. If this was a latitude and longitude spherical function defining what the world looks like around me. You can see there's a door to this room. There are some windows here. You can then say, when I'm drawing to the screen, the texture mapping I would like to implement, the computation conceptually, is that when I consider a pixel on this surface, and I'm going to pretend this teapot is shiny or has a shiny component, very glossy, then for my viewing direction, what I want to consider is the reflection direction off the teapot. And I want to take that reflection direction and say, oh, what's the color of the room that I'm in that direction? This would be like reflection mapping the environment onto the teapot. And if you imagine turning this teapot, right, it's not going to be this window that's glued onto the teapot and sticking onto that part of the teapot as it's rotating around. No, as you rotate the teapot, the reflection of the room will stay in the same location, but it'll look different, like when the spout passes over that location. It will look like a shiny object in this environment map, or in this visual environment. Okay, so environment mapping. Oh, by the way, this lookup is also totally different than before. What's the lookup function here? For every pixel location, we need to calculate a reflection direction. We'll talk about that kind of mathematics, okay? It comes up a lot in ray tracing, similar kinds of computations. And we have to calculate a reflection direction, and then we have to take that reflection direction and say, what pixel location in this environment map does that correspond to? So there's going to be a whole bunch of different mathematics at that texture lookup call, okay, or that sampling. If you apply that technique, you don't have to just draw a picture by hand. This is like the very early work on this environment mapping. You can take photos, okay? You can take a gazing ball. This is a famous picture by Escher that shows the concept. If you have a gazing ball like a mirror and you look into it, you can actually see the entire room reflected in it. You can take pictures of famous locations. This is Uffizi Gallery in Florence. This is Grace Cathedral in San Francisco. This is the eucalyptus grove on campus. Okay, this is in Rome. You can take these light probes, as Paul Debevec called them, and you can use those in environment mapping. And if you do that, then you can create renderings. For example, this is a synthetic scene here. There's a glass sphere. There is, I guess, a marble sphere, a gold sphere. I don't know, there's this table that's sort of glossy, and all of it's embedded inside this photographic environment, in this case of Grace Cathedral in San Francisco. And we're rendering all of these objects using that environment light, okay, that environment texture, in order to make them look as if they exist inside that lighting situation. Okay, really cool stuff. This can really increase the realism of pictures. There are ways to represent that same kind of function, that environment map, instead of latitude and longitude, which has, sort of some singularities of the poles, the North Pole and South Pole, that can cause some sort of like a difficulty in anti-aliasing. You can also represent them as a cube map. This is just a bit of cute math I want to share with you. It just turns out to be a really nice solution for this, or a nice representation for an environment map. An environment map is just a spherical function. It just says, if I'm at a particular location, what does the color of the world look like in every spherical direction around me? Okay, it's a spherical function. You could say instead of a sphere, let me just project that onto a surrounding cube, conceptually speaking. And then it's the exact same function, but I'm going to store it in memory just by 6 images, right? The images represent the value of that projected function onto the surface of that square for each of the 6 squares of the cube faces. Okay, what does it look like? This is the one for that one of those environment probes, the light probes that I showed you taken by Paul Debevec. This is the one in Rome at St. Peter's Basilica. Okay, so this is the cube. So if you imagine sort of folding this up into an enclosing cube and thinking of that defining in every particular direction from the center of the cube what the color of the lookup is, then this is an environment map representation. This is quite common. And in fact, there's in all GPUs, I mean, there's graphics, hardware acceleration. So the silicon that's dedicated to, if you give a vector direction at the center of a cube like this, and you address this cube map with that kind of a angular direction, it's all hardware accelerated to look up the corresponding pixel location in a cube map structure of this kind. And you can say, here's the cube map by just providing 6 images and telling the GPU to interpret it as such. Okay, so that's a bit about environment mapping. Let me tell you about a really different application of texture mapping, which again, just think of it as bringing data, right, to the detailed computations in graphics. Displacement mapping. You could store in the texture the perturbation to the surface position as opposed to the color of it. So in this scene, for example, which you can see if you look closely, has a lot of like fine details, like little bumps, if you can sort of visually perceive them, right, in this paintwork. There's a way to represent that so that you have a base surface which is defined in terms of very smooth geometry. It's modeled kind of, mathematically perfectly, as you can see here. And then you could have a hand-painted displacement map texture where the intensity of the images here in this texture image represent like a displacement along the normal direction, like a dent height or depression depth. And you could tell a graphic system, hey, this is what I want to do, is I want to apply this displacement map onto this object, and I would then be defining an object that has a lot of microstructure, okay, geometrically speaking. This is a really nice idea and simple to describe and conceptualize. It's proven to be quite hard to implement efficiently in graphics. So for decades of, the heart of like decades of, really high budget movies, games, displacement mapping was not a very common thing for high budget games, rather, not movies. This was not a very common technique because it's really hard to accelerate. And in contrast, there are other techniques that really, I think, also show the kind of creativity that can happen in terms of the computations happening at a detailed level that use texture data. This bump mapping is related to displacement mapping. But instead of storing and interpreting the data in the texture image as the displacement of the surface, you can think of it as like a perturbation of the surface normal. And you could choose the perturbation of the surface normal so that it would be consistent with as if the object at a very detailed fashion had bumps or had displacements according to a displacement map. Let me show you what it looks like. Here's the base geometry. In displacement mapping, we stored the displacement of the surface. So you can see on the silhouette, for example, that it's actually changing the shape of this base geometry and gives it a lot of fine detail. In the center, this image looks a bit similar to the one on the right in the internals of the object. You can see it looks as if it's bumpy, right? Almost as if it has this kind of displacement. But you can see if you look closely at the periphery that it hasn't changed at all. It has the geometry that's shown over here. The difference is that it's a lot more efficient to implement bump mapping. And for decades, it was far more common to do because it doesn't change rasterization. You get the same XY sample locations for every triangle in the geometry, and each of those interpolated positions, we do a calculation that uses the surface normal that's perturbed by using values from a texture map. And I explain what's sort of different. Okay, perturbing normals versus perturbing positions, and what's missing is the silhouette sort of shape there. Let me switch gears and give you another flavor. I think this is so awesome. This is 3D texture mapping. So we talked about 2D texture mapping so far. In this case, you can think of defining some kind of function in volumetric space. There's different ways to get that data. I'll show you a few examples. In this case, actually, on top of being in a volumetric space, the value of the function itself is defined procedurally. Okay, in this case, it's using some kind of randomization scheme, some kind of noise generation scheme, as well as a way to sort of combine it over different, what are called octaves of noise in order to generate procedural noise. This is called Perlin noise. very famous in graphics. So that's you define a 3D texture. After that, you can say, let's consider some kind of object, but draw the values on the surface of that object by sampling into the 3D texture, not taking a 2D texture and pasting it on. So in this case, you just have a sphere. You draw the surface of that sphere. At every surface position, you say, at this XYZ position, I'm going to look up into the XYZ position in the volumetric map. In the volumetric map, we're like, hey, we're going to represent these as like sort of the colors in some marble or something like that, as you can see. And voila, you're going to get what looks like a sphere that's carved out of marble or a vase that's carved out of marble, that kind of a thing. Okay, pretty cool, pretty neat, pretty different way to think about bringing data into the computation. Where did my next slide go? Actually, I want to go here. Let me observe, there's other ways to combine something we'll talk about later in the course, which is more realistic shading, such as shadows, micro shadows on surfaces. You can do something called ambient occlusion calculations to calculate kind of the micro shadowing over like wrinkles in a character's skin, for example. You can store that in a texture map and then apply that kind of pre-computed shading from an expensive method. You can apply it in real time onto an object to help increase its realism in a lot of ways that are very hard to do with real-time computations alone. But coming back to the 3D texture thing for a second, I wanted to also share with you that you can define it creatively, like in that marble, carving things out of marble example. You can do it for pure creative purposes, but you can also use it for scientific visualization or medical imaging visualization. So here's an example that takes a CT scan of a person's head. The CT scan gives you the density, right, at every position in the volume. You have a 3D volume, and then you can say, why don't we try to make a picture as if, someone asked the question, is this marching cubes? If you haven't heard of marching cubes, don't worry. That's a way of taking the volume and converting it to polygons, okay? By finding all the polygons that represent an isosurface and then drawing that. That's another way to visualize volumes. This is not. This is using texture mapping by saying, let's take the CT scan and imagine that all of the densities that correspond to, say, flesh in this case are transparent. Let's imagine that all of the densities corresponding to bone are made out of metal. And let's imagine that the surface of the skin, so the interface between flesh and air, the density of air, let's imagine that there's a very fine, like sort of, semi-transparent glass-like surface at that location, okay? Then let's try to draw using graphics, in graphics techniques. Let's try to visualize that. That's exactly what's being shown here. This is called volume rendering. And the way that it's done, implemented at a very high level, I'll summarize, is by drawing many, many slices of polygons through the texture volume. The texture volume contains the CT scan in this case. And as we draw all these slices, we're going to rasterize pixel locations on the screen that correspond to different depths from back to front through this volume. And then we can calculate using the definitions I described above, sort of saying these things are transparent, these things are solid, and these things are made out of these materials, and these other things are made out of these different materials. We can shade each of these samples as they're kind of going through and accumulate them according to the transparency and build up volumetrically from back to front this image. Okay, so this is called volume rendering. There have been very few, if any, volume rendering projects in class. For a final project, if any of you are interested in this, we could chat more. I think this is a really interesting project and applying a GPU for real-time volume rendering. Okay, that's the end of texture. Okay. Some things to remember. Maybe I'll summarize this one since we spanned a couple of lectures for today. So there's many uses of textures, which are giving you a whirlwind tour of at the end here. Think of it as bringing high-resolution data to fragment calculations. You can store colors, normals, lighting on a sphere, volumetric information. Sky's the limit for your creativity. How does texturing work? We have to have texture coordinates applied somehow to our scene. If we're applying across the surface of triangles, which is very common, we have to interpolate the coordinates, so barycentric in the case of triangles. We then texture sample into the texture images, and we have to be concerned with the sampling pattern, the frequency of it, and aliasing. And then bitmaps are developed to provide a texture filtering hierarchy that if we do a level calculation correctly, that we can end up sampling at rates that are going to avoid aliasing with a very efficient computation. I also touched on you're going to implement trilinear interpolation, and I mentioned anisotropic sampling. Okay. All right. That is texture mapping, and brings us to the end of the stuff that is going to be applicable to your first assignment. Okay. But still conceptually really closely related to all of this stuff, which I want to tee up and then we'll pick up next time, is putting together all the things that we've talked about in class up to this point, and putting into a picture of the rasterization pipeline. This is like how you would address something like a GPU. So when I say rasterization pipeline, that's the OpenGL DirectX style a way of addressing graphics that has been very common in real-time graphic systems. Maybe before I do that, let me just see. Yeah, there's a question here, one from Eric. Oh, thanks, Eric. Yeah, great question. Are different kinds of environment maps better suited towards different tasks? Yes, for sure. So for example, a latitude-longitude map is really easy to think about mathematically. And if you're trying to define functions on the sphere, that's a very natural one often to use polar coordinates for. So that can be useful for that sort of reason. Cube maps are really efficient to look up on GPUs, and they don't they have really good sampling properties compared to without singularities, like at the poles, North Pole, South Pole, compared to like latitude, longitude maps. So cube maps are common for that kind of a thing. The gazing ball representation that I showed you is actually really common in graphics because that's an extremely convenient way to capture photographic environment maps. It's literally you take a gazing ball, like a shiny mirror ball, and you put it on a tripod somewhere in a scene, and you take a picture of it. Okay. Converting between any of these representations, of course, is easy in principle. It's just looking up the corresponding positions on a sphere and converting it from one format to another. Okay. Let me start us on the rasterization pipeline. So what have we covered so far in the course? We've talked about positioning objects and the camera in the world. And we've talked about computing the position of objects relative to the camera. We've talked about projecting those objects onto the screen. We talked about sampling triangle coverage, so scan converting or rasterizing. Think of it as rasterizing. Scan converting is it's a synonym, but we haven't talked about rasterizing the object geometry, triangle by triangle, to calculate the sampling on screen space pixels. We've talked about interpolating attributes across triangles, such as colors or texture coordinate values. And we talked about sampling texture maps in order to put it onto the screen, okay? So what are we missing so far here? Let me show you a picture that encapsulates a few things. This doesn't have texture mapping, focuses on the other stuff, but I think this is illustrative. What's happening here? Oh no. What happened? Oh, there it goes. Okay, video wasn't playing at first. So I hope you're seeing an animation of some rotating cubes in space, or things that might look like rotating cubes. You see that? Is it coming through Zoom? Yes? Okay, good. Wasn't playing for me at first. Okay, so there's some things that, well, I call them rotating cubes. Actually, I probably shouldn't have done that part, biases your imagination a little bit, but there's something that actually is supposed to be rotating cubes in space, but you notice it looks really weird, okay? So what are some of the things that kind of look weird? Well, based on sort of the implied sizes of these objects, like this blue one, for example, looks like it's getting closer because it's getting bigger, okay? But when it gets closer, the closer objects aren't blocking the further ones. Can you see that? The further one was blocking the closer one. It just looks kind of weird. Also, these objects don't look very 3D. They kind of look like cubes, kind of not. They're not shaped. So what's missing? Well, at least one of the things that's missing is they're not shaded according to an implied lighting. and they're not occluding each other. They're not blocking each other visibly in the correct kind of a way. So if we just add those two things, shading according to a lighting, implied lighting, and materials implied on these surfaces, and we handle what's closer and further and draw closer stuff on top of further stuff, it just looks a lot more convincing. Okay, so I'll go back again. This is sort of with stuff we've talked about in the course up till now. And then add a couple more things in this lecture and describing the whole pipeline and be able to do things like this. And that's where we're going to stop today. What else are we missing, though? We're still missing a ton of stuff, okay? And that's going to come later in the course. So what else are we missing? Look at this picture. This is not a photo. This is a rendering, okay? Man, it's like, wow, we can make pictures that look super, super realistic, not just cubes floating in space, okay? So what do we see here? We see lots of geometric detail, right? I mean, there's like fine details and all this like cutlery. We see a whole bunch of different materials, enamel that's shiny. We see, stuff like this yellow, like custard. We see shiny metal. We see a cloth. Also notice we see lots of different lighting effects that are happening here too. Soft lighting that is bouncing, around the different types of glossy material, casting light from one object to another. Some shadowing effects. We also see kind of depth of field effects. It's kind of blurry in the background. If you look here and sort of notice, right? See this cloth here is sort of an optical blur on it, but it's very sharp here. All these kinds of things. Okay, so this is another picture. We're also missing things like motion blur kind of effects, complex materials, complex lighting. So to summarize, what else are we missing? Surface representations, lighting materials, camera models, lots of detail in there, okay? And this is a course roadmap for the next couple of modules, big modules coming up. Where are we so far? We've had intro, rasterization, transforms and projection, texture mapping wrapped up today, and we're gonna start visibility, shading, overall graphics pipeline. That'll finish up our module on rasterization pipeline. Okay, so I'm almost done with that. Then we'll have a module on geometric modeling, smooth surfaces, curves and surfaces, as well as lots of triangle meshes and how we deal computationally with that. We'll talk about lighting and materials, including global illumination and how we can handle things with all the kind of the material sophistication and lighting sophistication, like that scene, the two scenes I showed as an example on the two previous slides. And then we'll have a module on cameras and imaging, getting into a lot of detail about that and incorporate those into our kind of ray tracing kind of systems, okay, to be able to understand how real cameras work and to be able to simulate their kind of visual characteristics on the computer. Okay, so that's sort of a bird's eye view for where we're going over the next little major parts of the course. But for today, as I mentioned, visibility, or did I say visibility, shading, overall pipeline. So for today, and then wrapping up next lecture. Visibility. What's visibility? It's about getting the picture right in terms of what is in front of other stuff and making sure that the closer stuff is visually blocking stuff further away. We call that occluding. To occlude something means to visually block it. Okay, so to get the occlusion correct. Here's a simple algorithm, okay? Let me just observe. They're very basic methods that you can use to do this. Painters have to do it all the time. So this is inspired by how painters paint scenes. They paint from back to front, and they overwrite in the frame buffer. Well, they overwrite on their canvases. We would think of it as overwriting in the frame buffer. So for example, draw the mountains in the background, then draw the meadow in front, right, of those mountains. Draw the trees on the meadow that also partially block the mountain. Okay, that's a painter's algorithm. For drawing a cube, you can sort of break it down a little bit and think about it a little bit more algorithmically. Draw the back face of the cube, draw this side, draw the bottom, draw this side. Actually, you kind of notice the sequencing in this case was, is a little bit important. Okay, some you can do in either order. You probably can convince yourself the left and the bottom could be drawn in either order, but the bottom has to be drawn before the right-hand side. Otherwise, this occlusion in this triangle here wouldn't be correct. And then you can draw the top, and you can only draw the front after you've drawn quite a few of the others. So if you think of the ordering of the visibility, it's sort of like a depth sorting in this case from back to front. And you have to draw all those triangles or emit those triangles in the scene from back to front. if you're going to follow a painter's algorithm. This is not bad, but it can be tricky to do, as you might imagine. You also might have to sort. And if you've got a scene with triangle meshes that are very dense, tens of thousands, hundreds of thousands, millions of triangles, sorting those in depth could be pretty expensive computationally. And let me also observe as sort of a technical, side note that, but sort of interesting mathematical observation. You can have unresolvable depth order if you just try to draw, triangle meshes sorted back to front. If this is sort of a pathological case, right? You can see that if you tilt the triangles just right, then they can all be mutually in front of the other, or portions can be mutually in front of the others. So to draw this scene and get it to work correctly, occlusion-wise, you'd actually have to take P, Q, and R, and you'd have to break some of these triangles up into smaller parts, okay? So you may not actually be able to keep your original meshes. You may have to remesh. So a simple algorithm conceptually, but, with some significant challenges to consider. Now, I'm going to tell you the answer that, the alternate solution, which is by far the most common algorithm, very brute force, works really well, is really won in graphics in a lot of ways. But let me just say before this is that you might have gotten the flavor that just the way I described it, if you're the kind of person that thinks geometrically, thinks about algorithms, thinks about, how to define mathematics for those kinds of problems, and you're into that kind of thing, you might be like, wow, that sounds like a really challenging problem, interesting problem. I'm going to say for the beginning of graphics, many people thought that graphics was about this problem, the occlusion problem. It was also called the hidden surface removal problem at that time. And one of the people that won, the Nobel, the Turing Award rather, our highest award in computer science for contributions in graphics and VR, amongst other things, wrote a really famous paper that was 10 hidden surface removal algorithms. So this is a really big topic in geometry and core graphics at the beginning. But it turns out one of the stupidest algorithms, which didn't even make the cut for the sophisticated 10 algorithms, is the one that dominates. Okay, so I'm going to tell you about that right now. But observe there's a really rich history to the geometric algorithms, problem. Z-buffer. This one, the idea is really simple, okay? In the frame buffer, we'll just store the Z value for the, that's the minimum Z value that's been drawn to that frame buffer location for that sample position. And as we draw a lot of stuff to the screen and we want the closest one to show up, then we can use the value, the Z value, or the value in the Z buffer at that pixel location to figure out whether the latest thing we want to draw is going to appear in front of everything else or not. Okay, we'll need an additional buffer for depth values. So the frame buffer stores RGB values and the Z buffer stores the depth values. Typically, the Z buffer stores depth in at least 16 bits of precision, if not 32 bits. It might be even a lot higher these days, depending on the graphics system as an option. And as an example, if you render this scene, this would be the picture you get on the left-hand side. And after you're done drawing the scene, you might have a Z buffer or depth buffer, synonyms, that looks something like this. Okay, so black for further in the world, white for closer in the world, closer Z values, and you can see in this shading, how this is changing continuously. Why did this inefficient algorithm win? Great question. So it turns out it's not necessarily an inefficient algorithm. It's very brute force, very simplistic. That didn't appeal to a lot of the people at the beginning who tried to find geometric algorithms and talk about sort of the computational complexity of that. In this case, it's expensive because you have to store some stuff for every pixel, but it's not much you got to store, but also you have to, you just draw the whole scene. And it's the simplicity and generality of this. You could just throw all the geometry at it. You don't have to sort anything, and it'll produce the right picture. That's the reason that it won. Let's just look at that conceptual description algorithmically. Okay, so just what's the pseudocode for this? Initialize the depth buffer to infinity. Okay, so the closest thing drawn at the beginning is all this stuff, nothing, everything's infinitely far away in the Z buffer. During rasterization, for every triangle T, for each sample X, Y, Z, and T, this will be rasterization. if the Z value of that sample is less than the Z buffer value at the current pixel location, XY, then we do something, okay? We update the color in the frame buffer and we update the Z value in the Z buffer. Otherwise, the current Z value is larger than the thing that's already been drawn on the screen. So the current triangle sample that we're considering drawing to the frame buffer is further away than something we've already drawn there. Well, then we don't want to draw it in front, and it'll look like totally wrong, right? The occlusion will be wrong. So in this else case, we just do nothing, not the closest sample. This is the pseudocode for the Z buffer. And I could show you the picture of what it is. It would only take me a minute, but in the interest of time, we'll have plenty of time next time to pick up here. I'll just walk through this pictorial picture of Z buffer next time, okay? All right, folks. Hey, good to see you all. And I hope that you have fun in the assignment and have a good weekend. And I'll see you again on Tuesday.